Hello, everyone.
Hello, good afternoon.
Good afternoon. Glad to see you all here. Looks like 16 of you are here. I think that's the magic number. So I guess we'll go ahead and get started. Anybody have any questions before we do?
Quick question, actually. You addressed this last class, but chapter 4 homework says that it's due on the 13th. However, we haven't covered chapter 4.
Right, and that's definitely not going to matter. Just remember, that's always your safety valve. If you know we haven't even started the chapter, then I can't. You can't hold me to. I mean, I can't hold you to those dates. Once I've covered it completely, then it's reasonable. So know that the dates are not correct for week 4.
Okay, sweet. Thank you.
No problem.
What about week chapter 3
for
though?
chapter 4, sorry. Yeah, the chapter 3 one should be correct in MyLab and Mastering. I'm not sure they're correct of what Canvas says, but it's definitely correct in MyLab and Mastering. I went through and set all that up properly. Okay. So hopefully it makes a little more sense.
But
on that
chapter
one.
4 is
right. We should do chapter 4. I think we're going to finish chapter 3 today. I might even still work some more problems next time, but essentially we've got all of chapter 4 all of chapter 3 will be done today. So 4 will start next time. But I think I have it to the 15th and the 12th for chapter 3, if I remember correctly. Might even be the 15th and the 19th. So I think that gives you ample time. There are 2 homework sets for chapter 3 though. And yeah, I think I did set it to the 15th and the 19th. Just trust whatever MyLab and Mastering says, as long as we've covered or at least started the chapter. Okay. Anybody else have any other questions? So hopefully y'all do take the time to watch those YouTube videos that I put in the week 3 folder or unit from Canvas. One, like I said, is called the world's greatest vector addition problem. Part of that is I take the time to add it graphically. And of course, there's also the graphic addition and the graphic subtraction. I take the time to do that graphically, you know, with a protractor and all that good stuff. But also part of it is that I use all the different terminologies and all the different notations for vectors and all that. So it should give you a good experience. Not only that, the one I did in your class was pretty good. Of course, remember, we did find that I made one mistake. I reversed 2 X and Y components, but we fixed it in real time. So it was ultimately correct. I'm probably going to share what I did with my class last night because that one turned out probably to be the best one. So I'm probably going to share that with all my 241 students as well. And I'm probably going to stick it on YouTube because it is the best one. But basically at this point, you should definitely know how to add vectors. Remember that I didn't actually talk about that in your class, but when you take the vector, like vector A, and it says, you know, 50 newtons at 34 degrees or whatever, when you're breaking that up into X components and Y components and putting the sign on it, that's called resolving a vector, okay? You're basically resolving a vector into its components, and then you can build back the vector up from the components by finding the magnitude and direction and stuff like that. So those are some terminology or some terms that you might run into that you want to be familiar with. Resolution of vectors. Remember, the term resultant always means the answer of a sum. So if you add any number of vectors and they ask you for the resultant, what they're meaning is add them all up, and the result of that addition process is the resultant. Okay. Any questions on any of that stuff that sort of bothered you?
No.
Gotcha. And I think your book gives some nice examples as well. Yeah, they talk about the unit vectors as well. They do the IJK. And like I said, it's perfectly fine if you use the X hat, Y hat, and J hat, or you can even save a little space and use the less than symbol and the greater than symbol. So what I'm going to go on to is showing you how to do projectile motion in vector notation. Not that that's really necessary, and I only do that occasionally, but it's kind of a neat perspective, and it gives you some idea of the holy grail of Newtonian physics is to write a R vector, which is a vector that is a function of time and maybe even position, that will give you the position of any object at any point in time. We sometimes just call it the X vector as well, even though we know it's X, Y, and Z, but you can use either one of those symbols and you just use a vector for it. The key to understanding all of projectile motion is the figure on page 321. So hopefully y'all got access to your book or access to the electronic copy of it. But basically it's a photograph that shows a ball being dropped at the same instant that a yellow ball is shot from the same height horizontally. So if you drop a ball and you shoot a ball horizontally, like this case, the horizontal ball and the vertically dropped ball will fall by the exact same amount at every instant in time. So what that shows you is that the horizontal motion and projectile motion is completely independent of the vertical motion. So you don't have to worry about what's going on in the vertical direction while you're working out the horizontal direction. So the way I often tell my students is imagine an ideal world like you grew up in, where you thought the sun was, directly overhead at noon, and you probably thought it was more or less directly overhead most of the day. Later you saw the sun. I hope I said sun, not moon. For some reason the word moon came to mind. But anyways, the sun, if you imagine it directly overhead, then all shadows would be cast perfectly vertically downward, right? So when you fire a projectile in that type of an ideal situation, that shadow travels just like a ball that's rolling on a perfectly smooth, frictionless horizontal surface, okay? All you've got to figure out is what component of that velocity is the horizontal component. So if I give you a velocity that's like 30 meters per second at 30 degrees up, then you take the cosine of 30, because that'll then give you the X component, and multiply that by 30 meters per second, and that'll give you the X component of velocity. And that ball is going to now roll forever as if it has no acceleration whatsoever. So when you're ignoring air resistance, literally the horizontal motion is just X equals V times T, or X equals V times T plus X0 if you chose not to use the coordinate origin as the first place it went. The rest of the motion, the vertical motion, is just like what we learned in the previous chapter. Go ahead.
What about the acceleration? Where does this fall into this little?
Right. So we do have an acceleration, but that's only in the vertical direction, and that's always an acceleration downward of 9.8 meters per second on Earth, or whatever the gravitational acceleration is on any particular planet. When we study Newton's laws, you'll even figure out where that 9.8 came from in a formulaic sense. It's related to the mass of the Earth and the radius of the Earth. So yeah, that part of the motion will happen. You are going to have an acceleration. So in that case, your Y, remember I said X is going to be equal to X0 if you don't set it at the origin, plus V0x times T, where V0x is the X component of the initial velocity. Well, the Y motion is going to be equal to Y0. If you didn't set it at the origin, then Y0 would be some other number. Plus, in this case, if you took up to be positive, then it'd be negative 1/2 of 9.8 T squared. And then if you shot it upwards, it would be positive. If you shot it downward, it'd be negative V0y times T. That's it. That's it. So you don't have to treat the two things interwoven so badly. You just say, okay, well, what's the time parameter I need? Well, if they're asking you how far it went to the left, then you just need to figure out, or how long it took you to go to 100 meters to the right of where you fired it. Then you just use that X equals V0xt plus X0 if you had, and set it equal to that final X value. That can solve you for the time. If that can be solved for the time, then if you need to know the height at that point in time, you just plug that into the Y equation, and that'll tell you the Y height. So that diagram, that fact that a ball dropped and a ball shot horizontally both fall at the same rate, allows you to completely disengage those two parameters, the horizontal motion and vertical motion. So what does that mean physically? Well, let me show you. So I'm going to turn on my document cam. Okay, and I've reconfigured my camera now that I can now write all the way down it without having to lift the page anymore. So what we have is a, dang it, I used the wrong pen again. What we have is a, where did my good pen go? That's not it, that's not it. I lost my pen. Oh, this is a terrible day indeed. Oh, nope, in my pocket. Okay, sorry about that. All right, so what we have is a x of t, which you could also write as r of t. That's normally what I write is r of t. That's a vector that's a function of time. And that's going to be equal to, if we do this, if we imagine our coordinate system like this, and this is x, and this is y, and you shot your projectile at some angle theta with some velocity v from the origin. Notice the tail of this is in the origin, and we're pretending this barrel is so wide that it's not going to alter the motion of the particle while it goes through the barrel. I'm just trying to make it look like a gun. So in that case, what you're going to have is the x component is just going to be v0 cosine theta times t I hat plus, in this case, you're going to say v0t, I put the t in a different place so I didn't have to use parentheses this time, sine theta minus 1/2 9.80 meters per second t squared. All that times j hat. Okay, and if you wanted it in 3 dimensions, you could add a y component as well and make this the z if you wanted. And the y component would just be like that as well. It'd be a v0 cosine theta, but you'd have to do something to project it down from the from the z-axis as well. So that's really it. You can do that. Now, if you wish to be a little bit more generic, like say your coordinate system is this and this, and you're actually going to fire it from this cliff right here. Actually, let's do it even more general. Let's say you're going to fire it from this cliff right here. This position being x0, y0. Then you're going to have r of t is equal to x0 plus v0t cosine theta I hat plus y0 plus v0t sine theta minus 1/2 gt squared j hat. Okay, so that's how you could alter it if you didn't have the origin. And there's something neat that comes from this, and that's part of the reason why I'm taking the time to show you. All these motions end up making parabolas. Okay, this motion would actually make a perfectly symmetric parabola. But when you solve this, sometimes you'll get weird answers like t being negative, and what that corresponds to is this motion back here that never happened. So this motion back here never happened, but all problems that you set up the math like this for always make parabolas, and the parabola in its entirety goes all the way back this way and this way. So when you're asking questions, you'll sometimes get things that seem aphysical, but what it is you took a bite out of the parabola and that was the reality, but the entire parabola is what the equations are established for. So sometimes you'll get that as well. So any questions on that? So let's
The
say,
last,
go ahead,
what is the last part of that, the equation there on the bottom say?
this one,
Yeah,
negative 1/2 GT squared, parentheses, J hat. That way it'll look a little neater. My little OCD daughter started using these and she's got me hooked because I'm OCD. Yeah. So anyways, that's your scenario. So let's imagine this. Let's imagine a projectile is fired at 100 meters, and I'll put a dot there, meters per second, so we can say it's 3 sig figs, at 100 meters per second at, let's say 60 degrees above horizontal. Okay. It was fired from the top of a 20.0 meter flat cliff edge. Assuming air resistance is negligible, what will be its max height above the canyon floor? B, how long will that take? In other words, after you fire it, how long will it take to get to that max height? And C, how far away from the base of the vertical cliff will the projectile land? And finally, E, what will be its velocity, which is a vector quantity, remember, just before impact? And I made my M into a N by mistake. Okay. So we got a projectile. We're going to fire it from some height. We're going to fire it at some angle. We're going to try to find its max height. We're going to find out how long it takes to get to that max height. We're going to find out how far away from the base of the vertical cliff. The vertical cliff just tells us that directly below where it was fired is where we want to measure it from. And then what will be its velocity just before impact.
I have the height.
You have the height. And now what did you get?
I got 402 meters.
How many meters?
402.
402 meters?
Yeah.
All right. Well, I will write that down as our prediction. Okay. So let's see. I'm going to set it up in a coordinate system so I can sort of make use of this vector that I just gave you guys. So there's my Y and there's my X. And what I'm going to do is I'm going to put my cliff right there and I'm going to say that's 20.0 meters. And then my projectile is going to do this. Let's do a red pen. Okay. What I want to know is H max. What I want to know is T at max. What I want to know is range. And what I want to know is V final. Okay, so that's all the things I want to know. So what I'm going to do is go ahead and write that R of T is equal to, I'm going to take 100 meters per second times T times the cosine of 60 degrees, I hat, I'll make that square bracket, plus my 20.0 meters plus 100 meters per second T times the sine of 60 degrees minus 4.90 meters per second T squared J hat, like that. So I know automatically that's going to be the velocity or the position as a function of time. So I can actually simplify that by going ahead and doing some computation. Of course, if we remember our 60, 30, 40 triangle, the 60 is supposed to be opposite square root of 3, which is about 1.7322 or 205, I think. The 30 degrees is supposed to be opposite the 1, and the 2 is supposed to be there. So you can see, for instance, that cosine 60 is adjacent over hypotenuse is 1/2. So this would be 50.0 meters per second times T I hat plus 20.0 meters. Now the sine 60, that's going to be 0.866, I believe 8660. Let's double check that. It's root 3 over 2. So square root 3 divided by 2 is 0.86602. Yeah, 0.86602. So this one's going to be 86.60. So plus 86.60 meters per second T minus 4.90 meters per second T squared J hat. Okay, sorry about that T getting in there squared and all that stuff. It's not supposed to be outside of the parentheses. I can fix it by making the unit a little smaller and then fitting everything in there a little nicer. Hold on. Okay. Now, the neat thing about this is there's several ways you can solve the problem. One way might come into your mind from just a pure math standpoint is we asked for the max height. Well, the way you find the max of anything is you take the derivative and set it equal to 0. So we could just take the derivative of this with respect to time, set it equal to 0, solve for the time. That should be the time T max. Or we could physically think about this and realize, wait a second, the horizontal component of velocity is always going to be basically this 50 meters per second. So it's always going to go 50 meters per second, 50 meters per second, 50 meters per second, 50 meters per second. But this vertical motion, which starts out at 86.6, is going to drop down to about 76.6 after 1 second, 66.6 after another, 56, 46, so on and so forth. You can see that you're probably going to take roughly 8.5 seconds to get to the max height. Okay. But the main thing is when the vertical velocity becomes 0, that's when you're at T max. Well, if I wanted to find the velocity, I take the derivative of this. And then you're going to set the y component of velocity equal to 0. That means you're setting the derivative of this equal to 0, which is the exact same way we got when we were thinking about it in terms of a math problem. So I'm going to do it the physics way and say that v sub y equals 0 at h max. So dr dt is equal to v of t. And I think you can see that's 50.0 meters per second I hat in the x direction. The derivative of this is going to be 0. You're going to get 86.60 meters per second for the derivative of that term. And then this term would just be negative 9.80 meters per second t in the j hat direction. So this is my Vx of t, and this is my Vy of t. So if I set Vy of t equal to 0, then clearly I get 86.60 meters per second is equal to 9.80 meters per second times t, or I get T max is equal to 86.60 divided by 9.8, which is obviously going to be a little bit more than 8.6 seconds. So 86.6 divided by 9.8 gives me 8.837 seconds. So that's actually the answer to part B. Okay. Now all I have to do is plug T max into Y. So this was X of T, and this was Y of T. So all we have to do is plug T max into Y of T to get H max. So when I do that, I go Y equals H max equals, now this time I'm going to take 20.0 meters, add to it 86.60 meters per second times 8.837 seconds. Notice how I'm using an extra digit, minus 4.90 meters per second times 8.837 0.837 seconds squared, and that should give me my answer. So I'm going to do 20 plus 86.6 times 8.837 minus 9.8 times 8.837 squared, and that gives me 19.90. Whoa. That gives me 20 meters. I did add the 20 plus 86.6 going up. I did do, oh, no wonder I did 4 point. Yeah, I did 9 point. That's what happened. Okay. I ended up multiplying by 9.8 instead of by 4.9. That's why I got the weird figure. I was like, there's no way that works. It doesn't. Glad I caught that. That would have looked stupid. And yes, you were exactly right. 402.63 meters. And really, this is 3 sig figs. That's 3 sig figs. And of course, that's 3 figs times 8 times 8 would be 64 times 4.9. So that really should be to the ones place. This one's also going to be to the ones place. So yeah, we should only round this to 402. So that should be called 403 meters. So you were right up to a rounding error. Good job. Any questions on that part? Okay, the last part, we've done what is the height above the canyon floor? It'll get 403 meters. How long will that take? 8.837 seconds. How far away from the base of the vertical cliff will the projectile land? Well, you can't use the wonderful symmetry that we used before. Remember when we were throwing objects straight up, if it took 8.837 seconds to get to the top, it would take exactly 8.837 seconds to get to the bottom. So you could just find basically y, or excuse me, you could find x of t in this case for twice 8.837 seconds. But because of this lack of symmetry, we can't do that. So what we got to do is figure out under what circumstances, under what time period, the y of t is actually equal to 0. So I'm going to jump to the back of, or excuse me, jump to the next page so I don't try to fit too much crap in one page. I'll put this right here, and I will put a meter stick or a ruler on the side of it to keep the wind from blowing it. Okay, I think I can just about see everything there now. Yeah, that's good enough. So now what I'm going to do is I'm going to calculate y of t equals 0 and find out basically how long it is aloft. That's called hang time. For instance, that's an important parameter for punters in the NFL. If you can get the ball to be up in the air, 4 seconds or something, that's a lot better than someone that can only do it for 3 seconds, because that gives your tacklers time to get there. All right. So what we're going to do is set y of t equal to 0. So I'm going to say 20.0 meters plus 86.60, carrying that extra digit, meters per second times t, minus 4.90 meters per second t squared equal to 0. Well, that's just the quadratic formula situation. And in fact, I can ignore the units if I really want to, but I like carrying them along so I can make sure I don't make any careless mistakes. So the quadratic formula is negative b plus or minus square root of b squared minus 4ac, all of that over 2a. I'm subscripting this t as THT for hang time. So negative b is going to be negative 86.60 meters per second, plus or minus the square root of b squared, that's 86.60 meters per second, that's going to be squared, minus 4 times a, which is negative 4.90 meters per second, times c, which is 20.0 meters. So notice the meters times the meters per second gives me meters squared per second squared, which is the same thing I have there, which it have to be because I'm going to actually subtract them. All that will be over 2a. And of course, 2a is 2 of half of g, and it's a negative, so it'll be negative 9.80 meters per second. So I'm going to compute the 86.60 squared. And that's equal to 7. Might as well say 7500. So negative 86.60 meters per second, plus or minus the square root of, I'm going to say 7500. And that's really only 3 sig figs, so that one's technically not a significant figure. Meters squared per second squared. Now minus and a minus gives me a positive, so that's good. I'm going to do 4 times 4.9 times 20, and that'll give me plus 392. Now that's 3 sig figs and 3 sig figs, which gives me just to the whole number. So I'll put a 0 there and make that like a doubtful digit. And then all of this will be over negative 9.80 meters per second. You can see what might happen here is now I'm going to get something that I'm going to have to round to the nearest tens. That's why I'm being careful with this. So now I'll take my 75 or my 7,500, my 7,500, and I'm going to add it to the 392. And I'll get 7,891.56. So I get negative 86.60 meters per second, plus or minus square root of 7,891.56 meters squared per second squared. Of course, this is only accurate up to the tens place. So that gives me 3 sig figs. I've got a unit there. So I'm going to take the square root of that. And I get 88.83. So I get negative 86.60 meters per second, plus or minus 88.83, which looks really close to 0 in the addition case, and that's meters per second as well. And actually there's an extra 4 on the end there, so I'll just put that there. And all this divided by negative 9.8. You can see that if you actually did negative and negative, you'd get a negative value. If I took this negative and the negative sign here, I get a negative there. But dividing by a negative, I'd get a positive. And that's the time we want, because otherwise I get a negative plus a positive divided by a negative. That's going to give me negative time. And as I hinted to you before, what that time would correspond to is the time back here that it took off, the time back here that it took off if the parabola was a whole parabola. So you could, for instance, add that to the time aloft, and you should get twice 8.83 seconds or whatever. Okay, so that's a neat little physical parameter. and this is meters per second per second. So meters per second divided by meters per second is just going to give me seconds, which is exactly what I expect. So I'm going to take the negative 86.6 minus 88.83. And I'm going to divide that by negative 9.8. And I get 17.90 seconds. Okay. This one, notice that's going to give me 3 sig figs over 3 sig figs. So I really should be able to call that 17.9 seconds. The other one, like I said, I'm just going to do it so we can play with it a little bit. But negative 86.6 plus 88.3, or excuse me, 88.83. Divided by negative 9.8 gives me negative 0.22755 seconds. That should really be the 3 sig figs as well. Actually, the way this works out, you're actually going to get one whole number answer and then only 1 decimal. So it should actually work out to be only 2. So all 3 of these are extra digits. So that should be about 0.23 seconds. I suggest, like I said, if you take the 17.901 and add to it that amount, that should probably be twice the 8.837 seconds we got earlier. So let's check that out just for fun of it. 8.837 times 2, that's 17.767. So if I add 17.901 and the 0.23, I get 18.1. So it's kind of close, not that great, but anyways, that's kind of a exceptional thing. If I rounded to 1 decimal place, it would actually work pretty well. But anyways, there we go. Actually, it was supposed to be, yeah, a negative. So yeah, that works. All right, so that's how long it's going to be aloft. That's the hang time. Now that I know the hang time, all I have to do is say, well, wait a second, if it's in the air for 17.901 seconds and it's moving to the left at 50 meters per second, then all I have to do is multiply that 50 meters per second times the 17.901. So R, the range, and that's why I use the R, we call that range. That range is actually going to be equal to 50.0 meters per second times 17.901 seconds. Again, those are both extra digits. And that's a decimal, and that's a separate 1 and a 7. So times 50, and I get 895.1 meters. So that's what the range is. It should land almost 900 meters away from the bottom of the cliff. Okay. Notice how I did that. I actually took the time for it to reach 0. For it to reach 0 in the y coordinate, and then I just used that in the equation for the x of t to find out what x was. And that's the way you solve all projectile motion problems. They normally ask you for things like the range, the max height, the time in the air, and sometimes the final velocity, which is the last part I got to solve. So any questions on that so far?
Yes, Professor.
Yes.
For the, you said the range was 895.1 meters. Isn't that
Right.
the range that the ball is going to travel in the x direction from the point 0 where it is launched to the, I guess, not the reciprocating, but the the other point that it hits
You're
zero.
thinking about there?
Yes, sir.
Yeah, so since I made my y0 20, then my coordinates down here, my coordinate origin is down here. So setting y equal to 0 forces it to be here. If I had used this to be 0, then yeah, that would have gave me that spot, which is not helpful. That's
Okay, that
also
makes
true
sense.
like when you deal with a punter, because the ball actually leaves the punter's foot some height above the ground. So if you just calculate automatically that time at which t equals 0, then you're going to, I mean, which height equals 0, and that's the origin, you're not going to get the right answer. You're not going to be off by much, but you're going to be off by some. But yeah, that was a great question, by the way. And that's the whole reason I set it up such that the origin was down here.
Okay, cool. Thanks.
You're welcome. Good question, Sam. All right, so now we're going to try to do part D. And part D is what's the final velocity? Well, the neat thing is we found that the velocity as a function of time was actually equal to 50.0 meters per second times I hat plus 86.60 meters per second with one extra sig fig there, minus 9.80 meters per second every second times t, all that times j hat. That is the velocity as a function of time. So really all we have to do is use the time ht, which is the time it's in the air, and we started t equals 0 at the instant it left right there. So that'll give me the time that it just about hits the ground. And I didn't actually put in a ground, so we're not worrying about it bouncing or anything weird like that. I would have to do extra F equals ma and all this crazy stuff. So you can just take the time at which it's supposed to hit ground, and that should give you the velocity at that point. Now you can tell this doesn't depend on velocity, and that's what I mean by the shadow of a projectile is always going to be moving at a constant velocity if you assume air resistance is negligible. So that's why it's just 50 meters per second there. So V of 17.901 seconds is equal to 50.0 meters per second in the I hat direction and 86.60 meters per second minus 9.80 meters per second. Now remember, part of this 9.80 times 17.901, part of that time is it slowing down to 0. And then the rest of it is it speeding up to a bigger negative number. So we're going to put times 17.901 meters per second, or excuse me, seconds there. And all this will be times j hat. So we're going to get 50. Written too small. So we're going to get 50.0 meters per second I hat. And then when I do the computation here, I get 86.60 minus 9.8 times 17.901. And that's going to give me negative 88.83, which we probably should have known that already from that. So it'd be minus 88.83 meters per second in the j hat direction. That's one extra sig fig there. So that's one answer. And this, of course, is in the unit vector notation, but I would like to see what it is in the magnitude and direction notation. So I'm going to draw a coordinate system again and build a vector out of the components. So I have an x component here, I have a y component here. In fact, my x component is 50. So I'm going to say the x component is this way, right? And then I'm going to say the y component is in the negative direction, and it actually should be a little bit bigger. So I'll make it a really long head. That's going to be 88.83 meters per second there. Because that's a bit bigger, that tells me this angle right here, which is supposed to be the real final velocity, the impact, that angle right there, phi, is going to be greater than 45 degrees. This is, again, another instance of always never solve a physics problem whose answer you don't already know or estimate. So I'm going to say that phi is equal to the tangent inverse of 88. Notice I'm not using any signs. 88.83 meters per second divided by 50.0 meters per second, which should give me 3 sig figs. So I'm going to say tangent inverse 88.83 divided by 50. And that gives me 60.6 degrees. And it's actually 60.63 degrees. That's one extra digit. And as we predicted, it is above 45 degrees. So that's something to give me a pat on the back. And then the magnitude, which we can either write with a vector symbol and then the absolute value bars around it are just as a symbol with no vector symbol on it. That's going to be equal to the sum of the squares and the square root of the sum of the squares of 50 and 88.83. So I do 50 squared plus 88.83 squared, and then I take the square root of all that, and I get 101.94 meters per second. Now this 88.83, when I square that, I'm just trying to see how big that would be. 88.83 squared. Yeah, that's going to be on the order of thousands. So basically, 3 sig figs is only going to give us the first 3 digits. So that's the thousands, the hundreds, and the tens. And then that's going to be added to 50 squared, which again is going to be up to the 10 squared. So I get 3 sig figs basically. When I take the square root of that, I get 3 sig figs. So this should actually be 102 meters per second. Notice it's not a huge difference from what the projectile initial velocity was, but that's a little bit of an coincidence, just because the 20 meters was so high, so low of a height compared to the overall height. It only was able to accelerate a little bit of time in that little itty bitty 20 meters. So that's why it came up that. It wasn't because of the symmetry that it was supposed to be exactly 100 meters per second, because remember, it wasn't a symmetric problem. Any questions on that?
Nope, that was cool.
All right, well, you can go ahead and if you wish to, and that's one of the lectures I normally give. So if you look at one of my old lectures, you can find it being done. But you can take these 2 equations as they are and then solve them for like the time aloft, the time to the max height, the final velocity, and you can get generic expressions that as long as the projectile leaves and lands at the same height, they'll always work. And you'll see that your textbook author does them as well. I recommend you have those, but unless they're numbered, you can't put them on your equation sheet anyways. But that does complete chapter 3 for us. You folks are free to go. I'll wait for the last person to leave in case you have any questions, but thank you for coming.
Thank you, Professor.
You're welcome.
Thank you, Professor.
Have a good weekend, Professor.
You too. Tristan, Kayla, Gerald, do y'all have anything? Noah? All right, well, I'm going to assume that y'all aren't there, so have a good one.
No, I'm here.
Oh, you are there? Okay. Did you have a question, Tristan, or are you just waiting for
Yes,
the last
I
person to
do.
leave? Okay, go for it.
Yes, yes. How often does do we ever really get an X acceleration? What would be an example of a good acceleration in X direction?
Well, if you actually take the derivative of v of t, you'll end up getting exactly 0x component and negative 9.8 for meters per second for the y component. So that's just another way of confirming to yourself that, yeah, without air resistance, the acceleration is always negative 9.8 in the y direction. But you could actually start from an acceleration being, a function of time, integrate that to get the velocity as a function of time, and then integrate that to get the position as a function of time. But that's two integrals, so you'll need two data points to find, for instance, the initial velocity and the initial position. But yeah, you can do that as well.
Okay, I was just curious because like in what situation would we have an acceleration in the X direction though?
It would be with air resistance. And when we get to Newton's second law and Newton's laws in general, I'm going to handle one of those. And that's also a problem straight out of your differential equations class once you ever take one of those.
I already took differential equations.
You did? Do you remember doing that where you had
Boyle's law.
dx over dt equals g minus something times v?
Yeah, we had used Laplace transformations, and we had used Boyle's law to use those two.
Yeah, Boyle's law is a nice differential equation. Yeah, this one was just a simple separable differential equation. It would have been like the first chapter you did. And that's what we're going to do. It's pretty straightforward.
Cool.
In that one, they usually just, I'll usually just treat a ball thrown straight up and calculate the position as a function of time with air resistance. If you wanted to do it the way where the X would have that component, it gets kind of nasty quick, and then we reserve that for a more advanced class.
Cool. But I actually built a program years ago for this exact example you made.
Oh yeah.
Yep.
That's cool. Like when you first took calculus, maybe?
No, it was when I took one of my first real engineering class.
Oh, cool. Well, that's good. Yeah, it's actually that's the wave of, I shouldn't say the future. That's been the wave of the future back in World War II, when they literally were using punch card machines and specifically one created by Xerox, even to solve the problems for nuclear weapons, and then later the space race.
Yep. All right, cool. You have a good weekend.
You too, Tristan. Gerald, Kayla. Anybody else have questions? All right, I'm going to sign out then. Have a great weekend. Enjoyed seeing you. Glad you could come. Bye-bye.